Yes, how's that going to work? Hey, Harry.
Not so much the quiz, but last class didn't we say that we were going to do homework number 7 for Wednesday?
Oh, indeedy. Thank you very much. Hiya. Look at this. Whoop. So let's put off that quiz then, because I haven't posted it and I haven't fully figured out how I'm going to work that. So I'm going to postpone that right now because you got enough going on that day. Sound good, everyone else?
Sounds good to me.
You can give me a status. Happy status. Woohoo! All right. Cool. So here, I'm going to add one more thing, and then we'll get started. Well, no, we still need some more people. Where are they all?
Derek just texted me saying he's trying to get in, but I think Blackboard's doing that same thing where it just spins for him.
Oh, okay. I'm going to here. I'm going to flip over to a different screen, and I'm going to send him the link again because I think it seems like the anonymous link works better for folks. Uh, do, 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 do. Cool. Okay. Blurb. Okay. So let's see. Missing Derek and there's Nick. Carter. Derek and Carter. Oh, here comes Derek. And he must be. Hey, Derek, did you use the anonymous? The guest link?
Yeah, Blackboard is not letting me get on anything virtual,
Okay.
and the links weren't working. Just nothing was working.
Oh, but obviously something changed.
Yeah, something worked. I don't know what, but something just changed.
Oh, that's fine. We came into alignment with the appropriate constellations. I don't know.
I guess.
Cool. Let's see. So I think we're just missing Carter. We'll give him one more minute. Huh. Yeah. So what do you find challenging there? I think most people are. I mean,
I don't know. It's just like I'm not there. You miss so much facial cues and hand waviness, I guess. And also, I don't know. It's just harder than actually being in class.
I'm experiencing the same thing with you folks too. So I feel you. Is that true across the board, folks? So two questions. Is it true for you? Uh, yeah, and in all classes for most people. Yeah, yeah. I mean, I'm finding. Well, I mean, obviously, it's more work for everyone. It's a lot slower going. Between that and like the rearranging all plans and stuff like that. I am like staying up until the early morning every day. And so yeah, I think we'll make some adjustments. Yeah. Yep. Cool. Anyone have good news from around you might want to share? Yeah, it's sunny. Yeah, try to find some time to get out. Obviously distanced, but get out and about. Took my kids bike riding. Do folks want to put on their video? Nope. Well, let's make it an option. If you want to, like there's no station that you do. You are welcome to do it, but you don't have to. Yeah, I had encouraged people to leave it off for bandwidth issues, but if it makes us all feel more comfortable, it would be nice if I can see, like, I'm struggling without cues from you folks to some extent too. So video helps. Also, just speaking up. Cool. There's Derek. Cool. I'm about to get started with everything. Just wanted to put up these announcements. Cool. All right. So yeah, for Monday, I had forgotten and I hadn't changed the homework. I going to remember to do that. We had said let's delay that till Wednesday, and I haven't updated the sheet, the assignment sheet. And with that change, I also want to push back the quiz some too. The quiz is going to be basically asking you to explain Maxwell's equations yeah, and do really simple problems. I haven't figured out all the mechanics for it. We'll try to do it outside of class. It'll be timed, but more generous than the time for in-class work. Let me get back to you about how that'll work. But so that's gonna be pushed back to Friday, though. Are we okay with that? Does Gauss's law? Yeah, we've got our Gauss's law indeed. So our four Maxwell's equations. There's Gauss's law, which is dynamical. There's a divergence of B being 0. Those are both still always true. The only thing that's different is our curls, right? We have these added terms where the curl of E and the curl of B depend on the time derivative of the other field. And we're going to see that coming into play even more once we start in on chapter 9. Today, actually, before I talk about today, so the other thing on Friday, I want to point out this right here. We're going to have our SMCM physics celebration, just chance to get together with other physics majors, stuff like that, honor some people who've done various things, and hear about some stuff going on, but mostly just hang out. Usually we do it, we get some snacks, have a big cake, and obviously it's going to be BYO food, but we can all hang out on Zoom. And you'll get extra credit for coming, just to get everything going, get everyone together. Cool. All right, so I'm going to put a box around this if it will let me. Hello. There we go. Cool. We'll get started where we left off. And so we were talking about energy, and we'd come up with Poynting's theorem that if there's, whoops, who that? Was that me or was that someone else? Poynting's theorem that if there's work done on charges in a volume, then it's got to come from either changes in the electromagnetic field or but we also have to, the other way the electromagnetic fields can change is if they carry energy out of the volume. So I'm going to write that out right here, and we're going to look at a couple different things with it. And then we'll do some problems with it in the end. Oops, let me get the right. There we go. So where we'd left off with a version of Poynting's theorem. Right, so the rate of change, and we integrate within a volume this term, which is, whoops, I left out my epsilon naught. The energy in the fields. Right. But the other thing we have to discount is any energy that the fields carry out. So this is the integral of the surface bounding the volume. Like that. So again, this is the mechanical, the change in mechanical energy of the charges in the volume. This is the rate of change of the total energy of the field, and here's energy being carried out of the volume by the fields. So we can identify a couple things here. So first of all, right, we called, oh, that's not right. I'm sorry. We called this whole thing right here the total energy in the electromagnetic fields. So we can write this out then, rewrite this as and again, this is, we can also, like we did in Fund 1, or like we did with our continuity equation, we can think of this as a big accounting tool. Let's just keep track of what's going on with the energy, and any change in energy has to be accounted for somehow. And so now, one of the things we can do, though, is we can actually look at some of these things right here. So for example, we called this term right here the Poynting vector. Oops. And we can also say a couple things about these right here. We can say that this bit right there, right, that total electromagnetic energy, actually we can identify it and say that this total electromagnetic energy, really this, we could write this as an integral over the volume of, well, I'm going to write it what we had from before. I don't know why, just to make it clear again. Because I'm going to write another way to frame this. And I left out the 1 over mu naught d tau, but we could also call this an integral over the volume of our energy density. So I'm trying to make that a lowercase u, and again, kind of hard with this in this medium right here. Got this lowercase u for our energy density as compared to the capital U right here. Total energy right here. Here's the energy density. So we have to integrate the energy density over the volume in order to get the total energy density in the field. I mean, the total energy in the field. And let's do one more thing over here. We can do the same thing with this right here. Remember that this W right here, right? This was the mechanical work done. It's mechanical. So the same thing, though, we can actually write this, make that equal to, and I'm sorry, this is kind of all on a slant and all that. Let's make this equal to, instead of an electromagnetic energy density, we can call this a mechanical energy density. Right? So now we've got these things where we've got volume integrals. So let's move this first term on the right, this term right here, over onto the left-hand side and gather stuff together, right? So I'm going to write that all up here. So both of them are time derivatives, and the one on the right, oh my goodness, neighbor's mowing. Pardon me a second. All right. So when we move the first term on the right-hand side over to the left, we get it's going to turn positive. So we've got time derivative, and then, well, actually, give me 1 second. Time derivative of both of them were integrals over the volume, and we can call this the mechanical energy density. Plus the electromagnetic energy density. So one having to do with motion and other configuration issues of the charges themselves, and then the other one having to do the electromagnetic energy density having to do with only the fields. And then on the right-hand side, we still have minus the integral out through the surface. Again, remember this Poynting vector is the energy per unit time per unit area that's flowing outwards. Oh, but we look at that right-hand term right there, and that, right, we're doing this over the surface area. So on one side, we've got a volume integral. The other side, we've got a surface area. If we want to make them both in terms of surface areas, then both in terms of the volume, then this is a perfect time to use the divergence theorem. And so that right-hand side right there, I can rewrite this as minus the integral over the volume of the divergence of S d tau. Right? So, okay. Now we've got an integral. This is true for any volume, right? So it's the volume part's completely arbitrary. So actually, if these two integrals are equal to each other, then that means, and then they're equal for whatever volume we choose, that means that the integrands, the argument of the integrals, have to be equal to each other. So we can rewrite this right here. Well, like, yeah, so basically drop the integral, and now since we're just talking about, we're not worrying about the spatial part, which we'd integrated out so we could do an ordinary derivative. Now we have to, the energy densities, we haven't integrated out their spatial dependence, so we have to do a partial derivative. So that's why I've switched to a partial. Okay, so what I'm going to do is box actually around two things here. If I can get this thing to work, I want to put a box around this bit right here and a box around this bit right here, where this is the one in fact that's a lot maybe more commonly used. So we're going to call this right here. This is another way to express Poynting's theorem. All right, so this is very much reminiscent, though, of the continuity equation we saw for charge. It's the same kind of thing, right? Where we said before that when we were talking about charge, pardon me, give me a second. That any change in the charge density was caused by a divergence, so flow outwards from the volume of the current density, right? So same thing in analogy. So change in the energy in the volume right here, the energy density in the volume has to be due to energy flowing outwards, diverging from that volume, right? Change in the charge density has to be due to current flowing out of the volume. So remember yesterday we started doing this by saying, hey, we're going to look at conservation rules. So conservation of charge was our charge continuity equation. Poynting's theorem is a conservation of energy. So the left-hand red box there, that is conservation of the total energy within a volume. And the differential form, though, the double red box on the right, that means for every single point energy in space, energy is conserved as well. So that's not only is the total energy conserved, but point by point throughout space, energy has to be conserved too. So it's even stronger. So we've got charge continuity, energy continuity, so charge conservation, energy conservation. The other kind of thing we could look at is linear momentum, and there is indeed something linear momentum can do. I'm just going to write this down here. We're not going to go through a whole derivation, all the details that there are in the book. We'll write down the expression for linear momentum. Yeah. Is that the solar sail thing? Yeah, right. Electromagnetic fields do indeed carry momentum. And so that's the idea behind solar sails. It's actually part of the idea behind laser cooling. Photons, if we start talking about fields and we actually quantize the fields, look at them and coming in little bits, little quanta called photons, then we can say we know that the photon, besides carrying energy, carries momentum. And so use it to slow down a moving atom and basically think of it like a collision between two objects, the way we did in Fun 1, between two cars, except the atom compared to the photon in terms of its momentum, the atom's at room temperature, then it's kind of like a big old train, and the photon's momentum's like shooting it with a bunch of peas, but if you shoot enough peas at it, you can stop that car. So same thing. It carries momentum. And the other thing, a lot of the rules for what kind of transitions you can have when you shine light on atoms and they absorb light and stuff like that, that has to do with the fact that the light carries angular momentum as well. So the textbook talks about that. So here we'll talk about linear momentum right now. So unfortunately, here's yet another P. So I'm going to do kind of like Griffiths did and do lowercase, but kind of cursive. So it's a vector, right? Linear momentum's a vector. Here, this is the momentum in the electromagnetic field. And again, I'm just going to present the result. The textbook has more about it. But look, it is proportional to the Poynting vector, right? And that kind of makes sense, right? If you've got a ball or a stream of balls or something that are moving along in a line and they're carrying linear momentum, then also they're carrying with them kinetic energy, right? And so they both point in the same direction, right? So our Poynting vector, we said, was the energy flow per unit area per unit time, but it's also, that's the direction momentum is going to be going to. Another way, it turns out that we're going to see that this is also equal to this right here. So this is our first hint of something that we've seen this before when we were looking at we had the two wires, two lines of charge. Yes, that is PEM. I tried to make it cursive so that it didn't look like a dipole moment, but yeah, sorry about the handwriting with this tool here. Remember when we had the two lines of charge next to each other, and so there's an electrostatic force between them, but as they move, we can think of them as two currents, and so there's a magnetostatic force between them. And we said, okay, at what point is the magnetostatic force as strong as the electrostatic? And it turned out that you had to go it only occurred when the lines of charge were moving at v equals c, the speed of light. And where did that come from? It came from putting together this mu naught and epsilon naught, right? And so we're seeing the same thing right here. Mu naught and epsilon naught, when we multiply them together, are 1 over c squared, the speed of light. And okay, kind of makes sense that that this is true because we know that light is an electromagnetic wave. But for folks in the 19th century, right, when they were talking about electromagnetic fields, you could say, okay, there's this properties of matter, but all of a sudden, they just everywhere they looked, they kept seeing this speed up, and it was independent of reference frame, right? And so, how could you have this speed popping up that was independent of reference frame? And this was a connection that eventually Einstein made and said that the speed of light c has to be independent of reference frame. And so here's kind of a foreshadowing of our of special relativity. So while I was talking and Camille was asking about this P, I forgot one thing here though. So this is linear momentum, but this is the momentum density. We should be a little bit careful, right? And so because we've got fields, right, it's not like there's a discrete object like a car carrying or a ball that carries all this momentum right here with this object. Field is distributed throughout space, and so we can't really we could integrate within a volume and find the total momentum carried by the fields in that volume. But what's more useful is to talk about linear momentum as a density. And so, yeah, you can integrate it up, though, to find the total carried by some region of fields. Yeah, momentum density. So again, it's how much momentum is there within a volume carried by these fields, because typically these fields extend out, throughout, beyond a confined region all over the place. So it's hard to talk about, all of them. Like, what do you do for these fields that kind of trail off going out to zero as you approach infinity? Right, so we can talk about, more of the momentum's carried in this region, less of it out here, less of it out here, less of it out here. And like we said, we can also have angular momentum. It's kind of hard to visual. Yeah, so are we okay? How about this? Are we okay with energy density? Right, so you can have more energy in some places where there's fields, right? And so it's kind of the same thing. The one thing that's a little bit hard is, right, this is a vector quantity, right? But yeah, we've got you. So if you think of any finite region, then that region, the fields in that region carry momentum. But if you're talking about a point, how much momentum is carried by the fields right at this point, well, that's going to be zero, right? Because that takes up zero space. But we can talk about, well, there's more at these points. These points are contributing more, and these are contributing less to that total right there. And so the yield term for that is momentum density. Same way we can have energy density, charge density, probability density. Whoops, we lost Camille. I hope she comes back. Okay. Oh no. All right. Hopefully she gets back. I'm recording the session. You can let her know that. Actually, what I'd like to try now is to try to replicate the group work experience. This is going to be a little bit tricky to do, and if it doesn't work, then yeah, we'll find something else. So if you on the tab where you have Blackboard itself, if you go to the resources area, there should be, excuse me, an energy and pointing vector practice problems. So give me like I don't know, a happy face when you found it and opened it up. All right. So not in the virtual classroom, but go over to, probably you accessed Blackboard from a tab, and I mean from a browser window, and then it opened up a separate window or separate tab when you entered the course room. So go to Blackboard, go to the resources area, and then down at the bottom should be the E&M worksheet. Leave on your happy faces or whatever once you have it. Just, I want to make sure that everyone gets it. So Nate's got it, Nick's got it. So we're waiting for, oh, Camille, you were out when I explained this. Welcome back. Sorry about your laptop. When you get, sorry, now that you're back, can you go to Blackboard itself, not the virtual course room, to the resources tab and open up the energy and pointing vector practice problems. Oops, there was a chat message. Blackboard's being a jerk. So Derek, you're struggling to get it?
Oh, yeah.
Okay. I can
It
share it
keeps
on.
booting me.
All right.
I'm gonna try to log in one more time, but it just keeps throwing me out.
Okay. I can also put it up on the screen. I just wanted folks to be able to have it. Next question is, let's talk briefly about mechanics. Do you want to break up into groups? Do you want to kind of, or would you rather work on it as a class? Here, let me set up a really quick poll. Polling, multiple choice. Break how to work. Break out in groups, because I can send people into their own group things together as class either. All right, cool. Yep, okay, cool. The polls there, go ahead, vote either way. Can you see what other people are voting?
No.
No, okay. So
Not until you close it.
Not until I close it. All right, cool. Thank you. So I have, so I've got 7 people who have voted in the poll out of the 8. Oh, I'm the 8th person. Wait, who are we missing then? We lost someone. Oh, we're still missing Carter. All right. Again, this is hard without seeing people's faces. Okay, so some people preferring together as a class, other people preferring either. So let's call that together as a class. All right. But I am going to, while I will do some of the writing, I want you folks to do the talking. Okay. So let's find a good way to do this. All right, so first of all, I'm going to erase the whiteboard, and then we're going to share that. That's not going to be what I want.
I finally got up.
Okay. Here,
wow.
I'm going. What? Oh, yes. One second. E&M worksheet. This one right here. Cool. All right. Now, let's see. We still have the whiteboard. Can I? And I apologize for this. We're application window. All right. Woohoo! All right. So you can see that there, but now am I going to be able to write on it? I doubt it. Zoom in. Yeah, I can certainly do that. Nope, that's not the zooming I want to do. Or let's go like this. Can I make it so that you can? I can. Give me a moment, though. I am juggling multiple things at once, getting used to all this stuff. Oh gosh. I can zoom in on anything. Yes, other people, you can zoom in on anything on your own view. Thank you, Derek. And I'm going to move not that way, this way. All right, but I actually want to, I'm going to close this down. So I'm going to do a couple. First of all, does everyone have this now? So if we talk about like problem 1, part A, everyone will know what that is about? All right. I'm going to stop sharing this, and I'm going to go back to a whiteboard that I can write on. Okay, cool. All right, so let's, I'm going to put this over here. So while you're looking it over, thinking over, that's supposed to be a 1. Is that someone else writing? Hey. It's okay. I'm going to have to put you all in lockdown. Keep it up. Yes. It's just like the first day in advanced lab where like half the class had their shirts up over the back of their head doing I am Cornholio. It's like, ooh, we're on video camera. We've got a whiteboard. That's supposed to be, say what? Yeah, they were. It was very much so. I didn't even make the connection that I don't know if it was intentionally. I think it just started because Jonah was cold and put his sweater or robe or something up over his head, and so everyone started mimicking him. But didn't make the connection that Cornholio always wants teepee. Give me teepee. It was pretty apropos. All right, give me a second here to clean up after you all. And all right, so let's do the first part. So what do we? Yes, Harry. What's up?
Out of curiosity, how do we erase our own stuff? Because I don't see an option to do that.
Is there an arrow thing? Like a in the upper left, an arrow tool instead of a pencil tool?
A select tool, maybe? Like the mouse
Yeah,
pointer?
select mouse. Yes, mouse pointer tool.
Ah, okay.
So that works. I don't know if the eraser tool, if you can use that. Yeah, you've got pointers. Like someone's pointing at stuff. So if you want to say, hey, what is that letter there? We're all in this together. So how are we going to find the energy density in this area? Mistakes were made.
Using the point.
Energy density? Not quite. I'll give you a hint. That's part B. So what's our tool, an expression for energy density? And we don't have any charges present, so first thing is there's no mechanical energy to worry about, no objects. All we have are fields. Do you want me to? Let's give it a symbol. So that's a lowercase u, right? So now, if you're taking your own notes, you can flip back and take a look at it on the previous whiteboard, right? So energy density, right, is proportional to each of the fields squared, with a different constant of proportionality. So all right, well, let's write this all out then, right? Anyone see what's going to happen with this? Yeah, UEM right there. Anyone see what's going to happen? A little clue about some collection that's going to go on? Oh, I don't know what I'm talking about. Never mind. I'm thinking of part D. Forget I said that. Well, yeah. All right. So we're going to do two things. So lowercase UEM is the energy density. So it is the energy per unit volume. Capital UEM is the total energy. So we could define a finite volume and say within this volume, this much energy is in the field. The energy density is going to be something that refers to a point. It's the energy per unit volume in a little point. So one way to think of it is we look at a little infinitesimal volume, right? Again, that's the physicist approach to differentials as we do in derivatives. As we do everything as infinitesimals. All right, so this part you folks can do, I think. Right, and so remember, right, squaring them, you can take the dot product with itself. It's one way to do that, and so we don't have to worry about the vector. The other thing is just, well, these are times a simple unit vector, so we can just square their magnitudes, and that works out pretty nicely. Okay, so we've got that common cosine squared factor. So if we wanted to, we can gather that there, but let's not and say we did for now. So one of the things we see, though, is what does this look like, right? Our electric field is, as we move through space, here, let me change to a pointer. As we move through space, cosine goes positive and negative. So as you go, for example, if z runs from left to right, it's going to go positive, negative, positive, negative, positive, negative. It's not moving along like a wave. It looks kind of like a frozen wave. And same thing with B right here. But the energy density, right, it just depends on the field magnitude, right, the magnitude squared. And so this goes, okay, it gets bigger and bigger and bigger, and then goes down to 0, and bigger and bigger and bigger, goes down to 0. Yeah, Derek.
Will the magnetic field be offset from the electric field because of the one you not before it?
It's no. So this it's just got, so the energy density from each of these things is going to go together, right? This term will get big when this term gets big, and this term will get small when this term gets small. But so what's the deal about the 1 over mu naught versus the E naught? Well, electric fields and magnetic fields are different kinds of fields, and so they have different dimensions. So the electric field squared doesn't quite have units of energy. It's proportional to energy, but it turns out that epsilon naught, this fundamental constant that's been popping up all along, this is the constant of proportionality to get it into energy. And the same thing, the constant of proportionality to get b squared of any kind of b squared into energy is 1 over mu naught. So you can't add E plus B. You can't add E naught onto B naught because they've got different dimensions. But here, these two terms both have dimensions of energy. Cool. And we haven't said how this field ends up like this. It just does. All right. So the Poynting vector, though. All right. What's the Poynting vector? Right. Yeah.
So would that be the 1 over mu naught E cross B?
Perfect. Thank you. All right, and so that's not too bad to stick in. And so we know it's just going to be the product. We could do this, well, it's going to be the product of their magnitudes, and then we have to use the right-hand rule, or we know that these two are orthogonal to each other. And so, okay, it's not too bad to do. 1 over mu naught, we've got E naught. I'm going to leave the cosine till later because we've got a cosine times a cosine. So we'll get a cosine squared. Give me 1 second, Camille. And then we've got an x hat cross y hat. X hat cross y hat gives us what? While you're thinking about that, getting ready to answer. What's up, Camille? Yeah, you have your hand up.
So where it's like 1 over mu naught E naught cross B, is that supposed to be a B naught too, or is that just B?
Both of them are supposed to be E's. Yes, thank you. That would be confusing if I write the wrong thing. Then yeah, there we go. And someone, I didn't see who it was. I think that was Nick. Said that x hat cross y hat is z hat right there. Okay. So we've got these terms right here. Okay, so let's take a look at C right here. So let's see what would happen if we had the same E right here. E is the same, but we change this cosine right here into a sine. Well, that's not too bad, actually. We're just going to write them out. Right, and so our energy density, we can just go straight here. The first term, the electric field, hasn't changed, so we still have this. Oh, sorry about that. And all that has changed is we've made this into a sine. And all right, same thing, 1 over mu naught. So E naught, B naught, and we'll have one factor of cosine. kz, and then we'll have another factor of sine, and it still points in the z hat direction. Okay. So we're going to treat these as two separate things, right? So, so for this bit right here, right, let's call this scenario 1. And this bit right here, this is going to be scenario 2. And for both of them, we want to check Poynting's theorem. All right, so how are we going to do that? All right, which version of Poynting's theorem should we be using is part of the question. Anyone have a thought? And we did these. Oh, we did these on the last slot on the last whiteboard, previous whiteboard. We had an integral form and yeah. All right. So Camille's saying she's looking at the equations already and saying, do we need the mechanical energy? And yeah, it's going to be kind of hard to do this without the mechanical energy. Let's try it without the mechanical energy, and we're going to see what's going on. All right. Oops. And so we're going to, the instructions talk about A and B. Really, let's look at scenario 1 and scenario 2. So let's take a look at, so Poynting's theorem, right, is going to be so the first thing we can do is let's take a look at for scenario 1, let's calculate the terms we can calculate. So for scenario 1, take the time derivative of this thing right here. Oh, that's not a pointer. You can't see what I'm doing then. Time derivative of this. This is something you can type. What's that going to be here? I got too many devices pinging. Oops. So let's do, as Camille said, we don't know the mechanical energy density. That time derivative, can we do that? So looking up at part A, time dependence, 0. Yeah, I don't see anything there. Cool. All right, let's do the divergence of S now. All right, so let's leave that one there. All right, so our divergence of S right here. So we look up at 1b there, and we know our divergence, well, this is in Cartesian coordinates, so it's going to be the x derivative of the x component, no x component, y derivative of the y component, no y component, and then the z derivative of the z component. Yes, we can do that. So, okay, 1 over mu naught, these are just constants. Take the derivative of cosine squared and you get 2 cosine kz, and then times a minus sine kz. right? And that was the z derivative of the z component. There is no, right, the divergence is, yeah, Harry.
Shouldn't there be a k out the end because we have to do the chain rule a third time?
Indeed, indeed. Thank you. Cool, right there. Okay. So cool. And we could collect that, but hey, let's wait on that. And so, does Poynting's theorem work? Well, on the left side, so far we've got 0. The right side, we've got something non-zero. But like Camille asked, we must have to be doing something to charges in order for this, because we know, well, we haven't shown it, but people before us have shown that Poynting's theorem holds. Right? We derived it actually. Yeah, we derived it, so we did actually show it. So, yeah, what's missing right here is what's going on to any charges that are present. We won't have just these fields by themselves without having something going on with charges. So, all right, we've got that. Let's do this other one. So all what we've got for problem 1, problem 2, the only thing different was is that we shifted the B field over slightly. Where did this extra Z factor come from? From a mistake. That's where it came from. So we did derivative of cosine squared gave us cosine times minus sine times the derivative of the argument, and the derivative of the argument is derivative of kz with respect to z, so that should just be a plain old k, right? So we could collect that k out front and the minus sign out front, but that won't show us all that much more. So let's do the same thing for case number 2. So same thing, if we look at the energy density in the electromagnetic fields, that has no time changing. It is constant in time. So this first and once again, right, we don't know what the mechanical energy density is, so we don't know how it's changing. And so we'll probably need that to actually reconcile Poynting's theorem right here. Let's take a look, though, at the divergence of the Poynting vectors. So the energy, this is telling us something about the energy density flowing out from every point. Okay, so that's this right here. So it's going to be something, again, there's no x or y component, so all we have to do is take the z derivative of the z component right there. I'm searching for my spot. There we go. All right, let's do it. Bunch of constants out front. And now we're going to get oh, hey, look, we've got a product. Let's do a product rule. So we'll do the first times the derivative of the second. So cosine kz, I'm going to stop writing those parentheses. Derivative of sine is also cosine. Cosine kz. And then right here, we're going to have the second times the derivative of the first. Sine kz times derivative first is a minus sine kz. Right. So another way to write this here, this was and we've got yep, and we're missing a k again. I just don't want to keep taking derivatives all the way through. And so over here we had 2k. Okay. So we take a look at this, and we had the same, if we integrated these up over a volume, right, we would actually have the same total energy. Because as you integrate a bunch of cosines squared, if the volume was big enough compared to kz, then you would just get a 1/2 from cosine squared and a 1/2 from sine squared, right? And so you end up with the same total energy. But our Poynting vectors are different, right? And again, one of the things, one way to look at that is our Poynting vector. Again, this energy flow depends on E cross B. And so for case 1, E and B both got big and positive at the same time, and both got big and negative at the same time because they were both the same cosine. But for case 2, right, E and B were out of phase with each other. So one would be big, but the other one would be close to 0. And then that one would be big, but the other one would be close to 0. So you would get a different dependence for it. So even though they were both kind of sinusoidal fields, by having them offset from each other, we had a very different behavior. Okay. And yeah, what's different? What was missing was the mechanical energy. Anyone want to write anything, ask anything about this? All right. So let's take a look at, let's set up a problem 2. I don't know that we'll have time to finish it all the way out, but let's set it up. Okay, so I'm going to erase this. 3, 2, 1. Pow. All right, so let's do number 2 right here. Really? You're killing me. Someone wrote 2 for me already. Thank you. I think. Oh, wait, before we do that, that doesn't work. All right, so here in problem number 2, we had we were taking a look at a coaxial cable. So you've got a long wire like this with the current going in it in this way, and then it's surrounded by a coaxial tube, right, with the current in that flowing down like that, the opposite direction, right? And this is actually very much like the coaxial cables by which you get your cable and stuff like that, except that that is not steady currents flowing. That is, oh, well, I'm sorry, this isn't a steady current either, right? That's an oscillating current, indeed. So let's take a look at these right here. So we're looking just in the region between the wire and the outer cylinder. We're not looking out past it. So in this area, we've got these things, right? So this right here is the standard form of what you would get of the magnetic field for a wire. In this case, it's I, our current is I naught cosine of omega t. And I should be putting that like that. So that looks just like the field from the magnetic field from a wire. And then, quick question actually before we keep going. This was in the area S is less than A, right? What is a magnetic field outside of A? Zero? Indeed, right. So how do we know it's zero? How do we know the magnetic field's zero outside of A? Besides the fact that when a physics professor asks a question, there's a good chance of zero. We proved it in class previously. Well, that's true. Can we recreate the argument even just verbally without a whole bunch of math? Yeah, go ahead, Harry.
And give it a try at least. If we do a Gauss's law type thing where we enclose the entire thing, both the cylinder and the wire, then our I enclosed will be zero because we'll have a positive I going one way and a negative I coming back the other way, and so therefore the B around that loop has to be zero.
Yeah. So the only correction I would say is that this is going to be Ampere's law, right? Not Gauss's law, right? But the current enclosed in the orange loop that I drew right there is going to be a net of zero, and so the magnetic field going all the way around that is going to be zero. But if we changed it instead, and made our loop on the inside, so if we did it like our loop just going like this, right, then that would enclose just the current in the wire and not the other one. And so we would have a non-zero current enclosed. And so, yeah, we would have a non-zero field like we see up here. Cool. All right, so let me just finish writing here. So for the electric field, again, the expression that we're given is the electric field that is, and this is I naught. Oh, gosh. Let's make those blue. So this is the electric field, again, in that region for S less than A, and it points longitudinally, right? And we can get this from Maxwell's, from Faraday's law, that we can take a look at the flux and draw a equivalent of an Amperian loop that goes like this in this region, and take a look at the flux through here, right? Yeah, and so here is our electric field induced by a changing magnetic field. And so we can do E going around this thing right here, given by the magnetic flux through it. Right. So here's the question, though. This was, again, for S less than A. What is the electric field, what is the electric field outside of this going to be? Cool. Oh, we're about out of time. Hello, I've got people going by. Yes. So here we go. Cool. All right. So all right, we're gonna do our. If we wanted to keep working on this, you know what I'm going to do? We are out of time. I will take 1 minute to kind of talk through this, and then I will also write out solutions and post them. But I'd like you to try to work through this on your own too, as for practice. You don't have to, but that's my recommendation. So what's the energy density in the region? We're going to, again, do E squared and B squared with the appropriate coefficients of epsilon naught and 1 over mu naught, respectively. Pointing vector, we're going to take a cross product. Which way is that going to point? Ooh, E cross B, so Z cross phi. Huh. What's Z cross phi? Well, we can, they're going to be orthogonal to each other, and so the third orthogonal direction is going to be the s direction. Yeah, plus r, right. So we're going to be going outwards, and actually I think, is that minus r? Yes, it's going to be a minus r actually, because they're out of cyclic order, or minus s, because we write s phi z. So now we've got our energy that seems to be flowing like inwards or outwards, but it's flowing radially. And so what's going on? Except for our cosine and our sine, those are changing sign. And so we're going to have this is going to oscillate, and cosine times sine, when we multiply them together, that's still going to be something that oscillates. So whatever that cross product was, whether it's positive or negative, when we take the product of cosine times sine, those are going to oscillate in time. Whereas the energy density, we're going to have a cosine squared and a sine squared. So those are going to go between positive and between positive value down to 0, back up to positive value down to 0. So they're going to be getting bigger and smaller at the same time that the energy flow is going to be going in and out, right there. And is there an induced EMF? Yes, indeed. This electric field here is the induced EMF. Right? So what we've got is the energy in this system is going to be going increasing, decreasing, increasing, decreasing, and meanwhile there will be energy flowing in and out through the volume radially, right? And so to do that, that means that this thing's going to be, that we could have in broadcasting. So does this affect the z-axis currents? It could indeed, although what we are saying is we are saying the currents are I naught cosine of omega t, right? It could make, if you had this EMF, that could try to alter it, but we are doing extra work against the EMF in order to maintain this I naught cosine of omega t. So we are adding mechanical energy. And that was a very good question, right? Because this is going to affect the z-axis currents. So that means that we are looking at mechanical energy of these moving charges going back and forth. And that's the third term in our Poynting theorem right there, right? So we've got the energy density going positive down to 0, positive down to 0. We've got energy flowing radially in and out from our Poynting vector calculation, and then, but we know that there's also going to be changing mechanical energy as the currents oscillate forward and backwards with the cosine of omega t. Cool. All right, so we're dealing with fields here, which are, again, more mathematically challenging, and they're harder to visualize, but we're still doing conservation of energy just like we did back in Fund 1. All right. Cool. So now you've got all the tools to do the homework for Wednesday, and I'll correct that on the various announcements and so on. That's it. I will post the write-up for this in a cleaner version for one, and I will see you all on Monday. But feel free to email me if you've got any questions. Cool. And Derek and Nate, I will see you over for outreach in a couple minutes. So take care, everyone. Harry, you're asking me about the SPS induction. So that's going to be that's by Zoom on Friday, this coming Friday, a week from now. That's part of the physics celebration that Dr. Dupree emailed about. But cool. Awesome. Cool. Yeah. So multiple things, multiple reasons to be there. Good stuff. All right. I'll see you later. Take care.